Hi everyone. In the previous class, we have seen the concept of logic gates. It includes like AND, OR, NOT, NAND, NOR, XOR, XNOR, like that. We have also seen the concepts of Boolean algebra, like what is the need of Boolean algebra, what are the properties of Boolean algebra, and we have seen various kind of theorems which we used for to simplify the expressions. Okay, like if we got any expression, that expression how to represent in the form of a circuit, and if we got any circuit how to express in the form of an expression, like that, right? And if we have an expression, that expression we can call it as a function. That function is one of the representation, like f of a comma b comma c equal to ab plus c. Right? This is a kind of function, right? The same function I can able to represent in another kind of form. We can call it as canonical form. This is also we have discussed. Like in canonical form, you are going to represent form of sum of products or product of sums that will be converted to standard sum of products, and product of sums will be converted to standard product of sums. And also finally we have solved how to convert standard sum of products to standard product of sums and vice versa also. Okay, fine. This is what we have seen, right? So now in today's class we'll continue further. If we have an expression called sum of products expression, sum of products expression, right? Sum of products means it contains minterms who are going to represent with 1, right? And as usual, normal variable x is 0, uh, sorry, normal variable x is 1 and x bar is 0, whereas coming to product of sums it is completely opposite, right? Yes, guys, sum of products means, can I say that this is the expression, like if I take ac plus bd, is this expression comes under sum of products? Yes, right? We are going to take each and every term as one product, product 1, product 2, product 2, and I am going to make sum of these products. I can call it as sum of products only, right? So with this expression, can I draw the circuit for this one? Yes. For example, if I take the input A and the input C, what is this? This is AND gate, right? So trying to perform multiplication. So A and D, and I'm trying to give two more inputs. One is B and D, and I'm trying to take like this, right? Oh, done. Right. Individual products are completed. Now OR operation there. OR operation symbol is something like this, right? So the output of A and C will be given to one input of OR gate, and output of B and D will be given to one input of OR gate. So your result is going to get AC plus B, AC plus B, right? So here, when you debug this, whether it is correct or not, if you are going to give certain inputs like 0, 0, 1, 1, what is the output you are going to get? 0 and 0 is 0, right? As this input is 1, that will be available here, right? 1 and 1, 1 and 1 is 1 in AND gate. Now on OR gate, 0 or 1, so this input will be available here, 0 or 1. So 0 or 1 means 1, so result will be 1. So like this you can able to analyze, right? So if you are going to construct truth table for this expression also, truth table for this expression also, for the input of 0011, your output will be 1, right? Instead of representing your entire data output in the form of truth table, where truth table contains both positive case as well as negative cases. Positive case means what? Positive case means which are producing the output 1, and negative case means what? Which are producing the output 0. Whereas your circuit is going to do the same. Whatever the possibilities are there to get the output 1, if you are going to give that input as input to the circuit, it is going to produce always 1. And what are the inputs that you are going to get the output 0? The same thing. If you are going to give that input to the system, it is going to produce the output 0, right? So these are the two alternative ways you can able to use, right? But thing is, for the system, you have to give in the form of a circuit only. Okay, fine. So now my point is, for example, let me try to take product of sums also. Uh, Product of sums. So where uh, normal variable is 1 and complement variable is, sorry, again cutting mistake, normal normal variable is 0, complement variable is 1. Here we have max term is there, max term is represented with 0, right? So if you want, like, it is represented in the form of pi symbol, and whereas it is represented in the form of summation symbol, right? Sum of the products. Okay, fine. So I will try to take the same expression but in the form of product of sums, right? So guys, if you apply, okay, no need to apply all those things. I will try to take another equation that is in the form of a plus c and b plus d, right? So can we able to express this in the form of circuit? Yes. A, first I will try to complete the a plus c. A is input, c is input, and we have an OR gate, right? First one is done. The second one is B is input, D is input, and we have an OR gate. We'll get output as A plus C and B plus D, right? For this, I need to combine with AND gate. You are going to get A plus C into B plus D, right? So if you are going to give the same input, double zero, double one, right? So double zero means 0 or 0 is 0, 1 or 1 is 1, 0 and 1 is 0, 0 and 1 is 0, right? See, because this is a different expression and this is different expression, that's why you're getting the different answers for same input. I hope understood. Okay. But in the industry, I have a question. I have a question for you, right? Here, if industry is following, if industry, I am asking you to implement the circuit for the industry is try to construct a circuit where in the form of sum of products or products of sums, and they are going to get so how many like AND gates are there? Two AND gates plus one OR gate. If it is in sum of products, if it is in product of sums, A plus C into B plus D, we are going to get two OR gates and one AND gate. Okay, guys. So as per of this example, it is okay. But what about if I give something like A XOR B, something like this? This is a kind of an expression where this expression I can write. So this is, I think, XNOR, right? XNOR. How? What is the equation for XNOR? Uh, like A bar B bar plus AB. This is the expression, right? So now it is available in the form of sum of products. Sum of products. For this sum of products, we need to make a construction, right? So for example, I will try to construct this as input A, this as input B, and whose AND will be resulted to AB. And A complement I am going to get, and B complement I am going to get by making it as NOT operator, right? Yes. Then I will try to make it using OR operation, right? Final result will be A XNOR B, XNOR B. Okay, guys. So what is the functionality of XNOR? When you are going to give two same inputs, your result is going to be 1. Result is going to be 1, right? So try to observe 0 and 0 is you are going to get 0. So as this is AND operator, right? Now here you will get 1 and 1 because it is complement. 1 and 1 is 1. Now on OR operation, 0 or 1 is 1, right? When you are going to give 0 0 as input, you are going to get 1 as output. 1 as output. Similarly, if you are going to take out 1 1 as input, you are going to get 1 as output. Try to substitute and solve it. If you are going to give 0 1 or 1 0, you are going to get 0 0, because this is the property or truth table of x NOR gate. For that, the expression is like this, right? How you got this expression? First thing, right? I will try to take these two parameters, a bar b bar or ab. For these two cases, I am not going to be considering, right? If it is product of sums, if it is product of sums, what I am going to do? I am going to consider these two. These two. Okay, that we have seen in the earlier video itself, right? Yes, fine. So here my question is, if they got something like a x nor b, they have to take how many like NAND gates? Sorry, two AND gates, two NOT gates, and one OR gate. One OR gate, right? So, but the thing is, as companies are moving from, as companies try to like try to construct the circuits, try to construct the, they don't know exactly how many number of AND gates are required, how many number of NOT gates required, how many number of OR gates required, like that, right? So that's the reason what the people thought that uh, is there any solution or not, they have to find, right? The solution will be available in the form of NAND gate, right? So guys, if you try to observe what the meaning of NAND gate, NAND gate is something like if you are going to give two inputs A and B, like its complement, right? NAND gate means AND plus NOT gate. Simply, we are going to represent it as like this. I hope you have seen the last class video. Okay, fine. So guys, we explained elaborately like the properties of basics of Boolean algebra, right? So guys, if you observe here somewhere, like, so what does this dot represents? This dot represents AND operator, this dot represents OR operator, right? Wait, whatever the expression that we have seen here in algebraic properties, all these I have explained in terms of and OR, right? All are satisfied. But what about in terms of NAND and NOR, right? They are also getting or not? They are also possible, right? So NAND I can represent in the symbol like this. Okay, right? So the properties of NAND are, it doesn't follow identity property. Identity property is not followed, but commutative property is followed. Commutative property is followed, and it is not going to follow associativity also. Guys, I hope you know how to like how to check all these, right? So the way that we did for and OR operators, you can do for NAND also, right? Similarly, we have NOR gate is there, NOR gate is there, which I can represent like this. So NOR means A plus B whole complement, meaning that OR plus NOT, plus NOT, which is also not supports the identity property, and it will supports the commutative property, and it is not associativity, not associative. Okay, fine. Similarly, I mean, why I'm trying to write here is, there I have seen and or operators, so the remaining operators I'm trying to write here, XOR and XNOR, right? XOR, you are going to represent the symbol like this, XNOR you are going to represent like this. Okay, fine. So it is also not supports identity property, identity property. It will supports commutative, and it will supports associativity. I mean, associativity means what? If I am trying to take something in one order, in one order, uh, and if I try to take the same thing in another order, both result will be same, right? So A XOR B XOR C. If I try to do like this first, which is equivalent to A XOR B XOR C. These two are same. That is the meaning of associative, right? For example, try to take out the values 110. What is A XOR B? A XOR B means when both are same, the result will be 0. Now, this 0 XOR with 0, 0. 0 XOR with 0 is 0 only, right? Now, try to do the right side part, right? B XOR C, that I have to give priority, right? So, 1, 1, 1, 0. 1, 0 is 1. 1, 0 is 1. 1 XOR with 1 is 0, right? Both are same. So, that is the meaning of associativity. Okay, so coming to XNOR, it also doesn't support identity property. It also doesn't support the identity property. It is commutative in nature and it is in associative in nature. So these are the some of the properties that are followed by all these NAND, NOR, XOR and XNOR. Okay guys, so here we are trying to discuss, right? So the industry aspect, like as industries are unable to find out how many number of AND gates, how many number of NOT gates, how many number of OR gates need to be produced, right? For that reason they thought to convert one kind of gate called NAND gate. And guys, I can say that AND or NOT, collectively we can call it as complete set operations. The reason why I am calling it as complete set operations means any kind of circuit, any kind of requirement, I can able to implement with the help of these things. Whatever the circuit it may be, whatever the expression it may be, whatever the thing it may be, I can able to design it with the help of AND or NOT gate. That's why they call it as a complete set operations. Okay, fine. See, if you observe how the industry is using NAND gate, so that is what I'm calling it as NAND realization. Okay, realization means it's a technical term. Realization means NAND gate implementation only. Okay guys, so NAND gate means what? Your result finally should be A into B complement to B complement. Guys, we have various kind of like gates are there. One is NAND, not inverter is there. Not inverter is there. What is the property of not inverter? If you are going to give A as input, you need to produce the output as A complement. A complement. For that, the basic symbol we have gone through is like this. Right? A, your output will be A complement. Okay, good. Now, can we implement this NOT gate with respect to NAND gate? Yes. Right. So I think while discussing the previous class itself, I have shown this one, right? See, if you are going to have that like NOT gate, try to observe. If you are going to have NAND gate look like this, right? So NAND gate symbol is like this only, right? Yes. NAND gate, right? Try to give, I am trying to give two inputs as A and A. What is A and A? A, that will be complemented to again A complement only, meaning that it will be acted as NOT gate, right? So I am trying to modify this structure like this, right? I am going to give A as input. I am going to go produce as A complement. See, this is the NOT gate representation in terms of NAND gate. Okay, fine. So if you try to take out the next kind of gate, AND gate. So AND gate means what? If I'm going to give A and B as input, I need to get the AB. I need to get the AB, right? Truth table has to be satisfied, right? See guys, so for our simplicity, how can we do this in terms of NAND gates, right? So NAND gates means what? In terms of complements it is available. So what I will do now, I will simply perform complement over complement. So complement complement cancel, again you are going to get the same thing, right? Can I do AB complement? Can I do AB complement? Yes. If I am going to have the two inputs AB, if I made like this, the result will be AB complement. For this complement, can we get the complement? Can we get the complement, right? How can we get the complement using NAND gate? This circuit, right? Then you are going to get AB. So this is the circuit you are going to use in order to replace AND gate with NAND gate. NAND gate. Okay. Fine. Similarly, we have OR gate is there, right? So OR gate means what? A plus B. How can we get the NAND gate relation? Because you have to define in terms of everything in the form of complements. But try to do that, right? I will try to make the complement of this A plus B whole complement, whole complement. So again you are going to get A plus B only, right? This I can be write it as A complement dot B complement whole complement, right? Now if I am going to have the input like this, if I am going to have the input A, from that input A can I get A complement? Yes, first done. Now if I am going to have input B, can I get B complement? Yes, I done. From this again whole complement, so simply you have to use again NAND gate. Now this is A plus B. So this is the circuit you are going to use for OR gate in terms of NAND gate, right? Let us take one more uh, XOR gate, right? XOR gate means what? It's like think A bar B plus B bar A bar B plus B bar A, right? So here, for example, if I try to construct, if I try to construct uh, the simple thing, right? Uh, Let me take A as input, I am going to get A bar as output, right? That I am going to give input as to the AND gate, right? A bar B. Okay. Similarly, B bar A, B bar A, right? So this is A you are going to get, and you require B bar, right? So I am going to make it complement B bar A. So finally you are going to get B bar A, and for these both I am going to construct OR operator. So your result is going to be A XOR B. Okay, fine. So as I said, so industry has to do what? This one OR gate is required, two AND gates are required, one OR gate is required. This is not. One OR gate is required. That is what they try to do, right? But thing is, as the requirement is changing, they has to like for example, they have implemented 1,000 AND gates, 1,000 OR gates, and 1,000 NOT gates. We don't know which one requires how many exactly. That's the reason. If you are going to implement all the things in one kind of a gate, then the company will produce only NAND gates 3,000 instead of producing one some or some and some not, like that. They will produce all NAND gates, so there is no loss, there is no problem for them, right? That's the thing, right? Okay, fine. Now we'll try to represent this XOR gate in terms of NAND gate. How to do that, we'll see. Okay guys, here the expression like A bar B plus B bar A, right? So as I am trying to write all in its complement form, I'm trying to write all in its complement form. I am trying to get with the complemented data, right? So A bar B, B bar A, I will try to add A, A bar. Is there any problem? A bar is 0, B bar also 0, right? Okay. Now I will try to take out the common B common from the first and last midterms. Then you are going to get a bar plus b bar. From the between second and third, I am going to take out the a as common. You are going to get b bar plus a bar. A bar. Okay, fine. Now can I write like this? Uh, this is like De Morgan's law, right? So De Morgan's law, if you are saying that a bar plus b bar, can I write like ab whole bar plus a ab whole bar or ba whole bar? Both are same, right? Ab whole bar. Now, see guys, try to observe why I have written, because now this one I can represent in the form of complement representation, like NAND representation. That's why I come across this particular procedure, right? So I will do like one kind of representation. Like if I'm going to have AB as input, I can get AB complement. That's why I came up to this procedure. Okay, one is done. But what about the remaining A and B? So that reason, what you can do now, you can just make it double complement. Double complement, right? So if you are going double complement, again you are going to get the same expression. Now try to solve this again. So main complement is as there, right? Inner complement I am trying to distribute over this data. Then you are going to get B into AB bar whole bar dot A into AB bar whole bar, right? So guys, try to observe now. AB bar is one component. AB bar is requires one NAND gate, and these two requires one NAND gate, and the whole complement requires one NAND gate. That's it, right? This is the simple way. So what you can do now, try to take out two inputs A, B. Those two inputs I am trying to give A, B. First I am going to get AB complement. AB complement, right? Is this AB complement done? Yes. So your output will be AB complement. AB complement. And this AB complement, I need to give it to what? B. Or let me do with A. A. First I will try to do this particular procedure. A. I will try to do it with A, right? If I am going to go with A into AB complement we got. For that, sorry, A into AB complement we got. For that I am going to have once again complement. Now this one act as this one. Similarly, B into AB complement we got. For that whole complement is NAND gate. This expression also done. This expression also done. For that you need to have again whole complement. Complement you are going to write, right? You know. That's it. This is the corresponding XOR gate. XOR gate for XOR gate in terms of NAND gate. In terms of NAND gate, right? If you want, you can able to solve this expression again, right? So here you are going to get uh, a b bar, a b bar. Okay. Here assuming that this has x and this has y, at x location you are going to get a into ab bar whole bar. At y location you are going to get b into ab bar whole bar, right? Guys, if you want, you can solve again x equal to a into ab bar whole bar. Try to solve this one. If you are able to solve this, you will get like I will try to write distribute over here a plus a bar plus b bar, right? Try to solve inner side. So complement is as usual. A into a bar is 0, a into a bar is 0 plus a into b bar, right? This entire terminology is 0. So you are going to get again ab bar, a is separate and b bar whole bar, b1 whole bar, right? This is the expression you are going to get. And what about the expression for y equal to b into ab bar whole bar, whole bar? If you are able to solve this one, solve this one, again you are going to get the same procedure, right? See, in terms of b they got as, in terms of a they got as b, right? If you try to solve this one, again you are going to get b into a bar whole bar, right? So if you are going to elaborately solve, so complement if you remove, that is b complement plus a. This is what? A complement plus b. So this x expression is, indirectly I am saying that a complement plus b. This y expression I am saying that this is b complement plus b complement plus a. Finally, finally you have an expression called z expression. What is the z expression again? It is trying to perform multiplication a complement b, b complement a for this whole complement. That is NAND gate, right? A into b whole complement, right? If you try to do this again, like do the transitive property, you will get. So a bar b bar plus a bar plus bb bar plus ab plus ab, right? If you observe this, these two are will be 0. So complement of a bar b bar plus ab, right? So for this, what you can do, so right, you know, right? So xr is complement of xnor is complement of xr, am I right? So or else if you try to solve this expression once again, you are going to get a bar b plus b bar a, which is equivalent to xr. So this entire, so in order to construct xr gate in terms of NAND gate, how many NAND gates are required? 4 NAND gates are required. 4 NAND gates are required. Okay, fine. Next one, XNOR is there, right? XNOR is what, ma? XNOR means if I have XOR gate, XOR gate. For this XOR gate, if you are going to add NOT gate, can we able to get XNOR? Yes, right? So simply I can say XOR plus NOT gate. XOR NOT gate, right? So you can simply draw this one. So for this NAND gate, if you are going to add one more NOT means what? Again NAND gate. So I'll try to draw the structure the same as usual. A B. Mm, there may be little bit variation in the diagram representation, but the outcome is same. Okay, this is what I will call it as XR. For this XR, if I am going to add one more complement, I am going to get XNOR. So final result will be A XNOR B. That's it, right? So in order to represent XNOR, how many NAND gates are required? 5 NAND gates are required. Okay, fine. Guys, if you are able to observe here, I have constructed NOT gate with NAND, AND gate with NAND, OR gate with NAND, XR with NAND, and XNOR also with NAND gate only, single NAND gate only, right? That's the reason this NAND gate I will call it as universal gate, one of the universal gate, right? Meaning that with the help of this gate, I can able to construct any kind of a basic gate. That's why we call it as universal gate. Okay, fine. Next, we'll see further gate, that is NOR gate. So actually, NOR gate is also an universal gate because with the help of this NOR gate, I can able to construct any kind of other gates. So finally, I can conclude that NAND and NAR are universal gates. So to prove this one, I am trying to do all these things. NAND realization, right? Next one is NOR realization. NOR realization. Okay. Try to take out the first one. So as usual, NOT gate. NOT means what? You need to have like if I'm going to give input A as input, you need to have the output as A complement. A complement, right? See, NOR means it is going to take two inputs and trying to perform OR operation over it and trying to perform complement. This is what the meaning of NOR, right? Meaning that if I'm going to give X and X as input, assume you are going to get X plus X whole complement. What is x plus x whole complement? X plus x is what? X only, again complement. So are you going to get that or? If you are going to get A as input, you are going to get A complement. If you are going to have X as input, you are going to get X complement input, right? Which is equivalent to X, you are going to get X complement. So NOT gate I can able to represent either in the form of NOR gate or either in the form of NAND gate, right? That's why I'm calling it as universal gates. Similarly, take out the AND gate. AND gate, right? See guys, AND gate means what? AB. If I'm going to give the two inputs AB, I need to get the output as uh, AB only, right? So try to take out double complement, AB whole complement, and trying to take the double complement, there is no problem. So A complement plus B complement whole complement, right? So guys, you know how to get the complement, you know how to get the complement uh, for A, you know how to get the complement for B, right? And you got plus, and then you have the complement, right? So this I can call it as, assume that this is as X, this as Y, this as Y. X plus Y whole complement, it is in terms of X plus Y whole complement. If it is X plus Y whole complement, can I do it with the NOR operator or not? Yes. So that's the reason I will try to do, right? What is A complement? How can I do that? If I'm going to have A as input, I will try to take it in the form of NAND gate. If I have B as input, I will try to take it in the form of NAND gate, right? I got A complement and B complement. Now, for this, I need to perform OR operation. For that, I have to go with the complement operation. So, you can take one more NOR operator. That's it. So this will yield to AB as output. Third one, OR gate. OR gate means if I am going to have two inputs AB, I need to get the output as A plus B. Get the output as A plus B, right? So guys, if I am going to give two inputs AB, if I am performing simply OR operation, I am going to get A plus B. But if I am going to have complement, what you are going to get? A plus B whole complement. For this, if I am going to remove simply this complement, will you get A plus B or not? Yes. That's why I am going to give certain again uh, to the complement A plus B whole complement whole complement. So are you going to get A plus B or not? Yes. Next, we'll see uh, X OR gate or X NOR gate, whatever it may be. You can do. You can take. Uh, but the thing is, from one, if we are able to do, you can get the another one, right? So I will try to do it with XOR gate, right? What is XOR? XOR means A bar B plus B bar A, B bar A, right? So here to get the XOR gate, so as earlier side example, I will try to add two values A bar plus B bar. Is there any problem? Nothing. Right? From this, I am going to take out the common A bar plus B bar plus A into A bar plus B bar. A bar plus B bar, right? Earlier, I required I required to represent in the form of sum of products because it is NAND relation. Now, to represent this in the form of OR gate, it require OR and gate relation. See, OR and gate. So that's why OR and gate means what? That should be compulsory product of sum, right? So I am trying to like this: a complement plus B complement into A plus B. Is there any problem? No, nothing. So now for this, I am trying to do some kind of complement again, double complement. If I do double complement, you are going to get one complement. That inner complement I am going to distribute A bar plus B bar plus B plus A whole, B plus A whole. That's it, right? Now observe this is like see, A complement you get easily using XR, B complement you can get easily XR. This entire terminal you are going to get with XR because it is in the form of one NOT gate. This is in the form of one NOT gate you can get, okay. And this is OR operation. For this operation complement is excuse me, OR operation with complement is uh, XR only, right? So I will try to construct the circuit for this. Try to do first I will try to do A plus B whole complement, right? So if I am going to have two inputs, A, B as two inputs, for this I am trying to get A plus B, and to get the A plus B complement I am trying to do this. So you got A plus B whole complement. Okay, now I need to get A complement and B complement as well, right? So to get the A complement, I am going to use one XR once again. You will get A complement, and I am trying to use B complement. For that XR is used. So here you will get A complement. Here you will get B complement, and I am trying to perform sum operation over it. Sum operation over it. Sum operation I did. For that sum operation, there will be whole complement. So again XR. So you got this term as well as this term. Now try to perform OR operation. If I'm trying to perform OR operation, I will get like this. But the thing is, there is a whole complement. So in order to represent XR using NOR gate, how many gates are required? Four NOR gates are required. Four NOR gates are required. Okay, fine. See, uh, if I take the XR, see, these are how many? I think five, right? One, two, three, four, five. Five NOR gates are required. Okay, fine. See, the same representation we can represent in another form, right? This is the common thing you can observe in various kind of textbooks. That's why I'm going to redraw the structure. A, B as input, this is one NOR gate, and another NOR gate. For this input, I'm going to get like this, and for this input, I'm going to get like this. So this is also A XOR BM. XOR, right? These two are same, right? If you are going to give the inputs, you are going to get the same outputs for these circuits. Okay, fine. Let us see the next one, X now. Okay, XNOR means what? A bar, B bar, or AB, or AB, right? So guys, uh, so try to do here. I am trying to make something in the form of like uh, this is like XNOR, right? Okay, so how can I derive this? So like I'll try to do. So can I write like this a bar b bar plus ab as a XOR b whole complement? Is it correct? Yes, right? Meaning that for XNOR, if you want to get, that is what I said, right? For XNOR, if you want to get, you can able just add one more complement. Just add one more complement. You are going to get a XOR b or not. Or if you remove this one, this particular part, you are going to get the exact thing XNOR. So I will try to do that, right? So I'm going to write. So this one, I will write it as a bar b plus a b bar, a b bar, right? So try to do like I will try to so instead of writing like this continuously, I will write as a bar b plus a b bar as like as earlier I have written a bar b bar whole complement, whole complement. I will try to take out the common as a complement. If I try to take out the a complement, that is a plus b. If I try to take out the b complement, that is again you are going to get a plus b. Guys, earlier procedure only I am doing. Right now. Now what I will do now, instead of writing like this, I will try to modify it in product of sums. Uh, what I will do, I will simply this complement should be same, and I will try to make it double complement. When I make it double complement, you are going to get, see, uh, do again double complement, then you are going to get a bar into a plus b plus b bar into a plus b. Okay, fine. Now try to distribute this, or else, I will write to chalo. You can write this equation, or else see, I will try to take a complement into a plus b whole complement. Can I do? Yes. B complement into a plus b whole complement whole complement whole complement, right? If I try to combine these two, as one, then are you going to get a plus b whole complement and the whole complement. If you are going to do the formula, right? So if you try to remove this like complement, you will get a complement dot a plus b whole complement, right? That's why I have written the syntax like this, right? Plus b plus a plus b whole complement whole complement whole complement for this between the plus is there, right? Now try to observe. This is one expression finally complement form. This is x plus y whole complement. That's the reason I have taken like that. Okay. So now try to represent the same circuit. So first I will try to do uh, the a plus b whole complement. A plus b whole complement, if you are going to do a b, a plus b whole complement, right? For that you have to take 1a, and you have to apply one second complement. So the first expression is done. And for b you have to take I think this input you have to take I am trying to take. So you are going to get b plus a plus b whole complement. A plus b whole complement. For the both, for the both, you have to do again. So I got x and I got y. I need to perform complement up. Guys, this should be XR, XR, right? Finally, you are going to get a XR with b. XR with b, right? So in order to implement XNOR, how many NOR gates are required? 4 NOR gates are required. 4 NOR gates, right? But in the industry or in some set textbooks, you'll observe this kind of syntax, this kind of circuit, right? This circuit will be parallelly written as like this. So now if I'm going to have the input a and b, here are going to get what? A plus b whole complement. A plus b whole complement. Okay. This input I am trying to give as one expression. B plus a plus b whole bar you got. Now the same input I am going to give for one more thing, that is a plus b bar whole bar. I got. For this I am trying to get. So this is also a XR b. XR b. Okay. I hope you understood clearly, right? So means if you would like to construct, if you would like to construct uh, XNOR gate, XNOR gate using NOR gate, you require 4 NOR gates. 4 NOR gates, right? If you would like to construct the same XNOR, the same XNOR with NAND, how many gates are required? 5 gates are required. You have to remember, this is important. If you would like to implement XOR gate with NAND, you require 4 NAND gates are required. This is like NAND only. If you would like to implement the same XOR with NOR, 5 NOR gates are required. Gates are required. I hope understood clear, right? Now, if you are able to observe, if you are able to observe, with the help of NOR gate, I can able to construct NOT and OR, XOR as well as XNOR. So this also called as a universal gate. Universal gate, right? So you can observe here, right? So if you are going to get any kind of circuit, if you are going to get any kind of circuit, you can simply construct that circuit with the help of either completely NAND gate or completely NOR gate. NOR gate. So company won't have any problem. They'll simply construct or they will simply produce either NAND gates or NOR gates. They won't bother about how many AND gates required, OR gates required, like that. Right? That's the simple thing. That is what the advantage of universal gates. Right? Yes. Yes, guys. So now try to observe. I will try to go with the first slide, what I have explained here. Now try to check here. If I am going to have this gate, right, AC plus BD, you are going to get like, you are going to represent in the form of AND or representation, and or representation. As under representation, you are going to get circuit like this. Okay, can we represent the same circuit with the help of NAND gate? With the help of NAND gate, that is what my question. Yes, we can do, right? So if you are going to do like that, if you are going to do like that, try to observe. For AND gate representation, for AND gate representation, how many NAND gates are required? How many NAND gates are required? Two NAND gates are required. So two NAND gates are required, right? In order to represent one AND gate, two NAND gates are required. In order to represent this AND gate, how many AND gates are required? Two NAND gates are required. In order to represent one OR gate, one OR gate, one OR gate, how many NAND gates are required? Three NAND gates are required. Three NAND gates are required. So total of 2 plus 2 plus 3, 7 NAND gates are required in order to represent the AC plus BD expression or the function, right? This is the general procedure. But the thing is, if your data is available in the form of sum of products form, the simple solution is, see, I will try to do. The simple solution is, try to take out the same structure. You are going to have AC, you are going to have BD. It will look like this, right? Look like this, right? Now try to observe. So this procedure is correct, perfectly fine. This procedure is perfectly fine. But thing is, can we able to reduce with less than seven NAND gates? See, maximum 7 NAND gates are required. This is maximum. But is there any solution to get less than 7 NAND gates? That is my question, right? Yes. Right. Try to observe. I am trying to make here complement. Complement. I am trying to put here complement, and I am trying to put here complement. See guys, if I am trying to put complement here and I am trying to put complement here, is there any problem? Again cancel, right? If I am trying to put complement here and trying to put complement here, is there any problem? Again cancel. Again cancel, right? Yes. Now, if you look into this particular syntax, this particular thing, what is the meaning of this one? Try to observe. If I am going to have two inputs, x and y, x and y, if I made like this, if I made like this, meaning is this is x complement plus y complement. So the input is x complement plus y complement. X complement plus y complement, according to De Morgan's law, you can do like xy whole complement. Can I write? Yes. Xy whole complement. Right? The same structure I will redraw like this. AC its complement and BD its complement, and I will try to redraw in terms of this dotted notation representation as, observe, x y complement, right? Xy complement was again as one NAND gate, one NAND gate. You are going to get again AC plus BD, right? So this particular representation is equivalent to this particular representation. This particular requirement, right? But here we require to represent OR and AND gates. Here we completely defined in terms of NAND gate. NAND gate. So what I did in order to convert any AND OR representation into NAND-NAND representation. So this is what I can call it as NAND-NAND realization. So in order to convert AND OR gate to NAND-NAND relation, the simple solution is you can simply put AND gates output with the complement and OR gates AND gates output with the complement and OR gates inputs with the complement, and try to replace the OR with the complements as NAND gate. That is simple procedure you have to do. But the thing is, if you would like to represent anything in the form of NAND gates, compulsory it should be in the form of under representation. And if you would like to represent in the form of under representation, compulsory it should be in the form of sum of products. This is the reason in the last class I have discussed the concepts of sum of products and products of sums. Okay. Now try to debug this. Is it going to produce the same output? If you are going to give 0011 as input, you have to produce, I think, output 1, right? So 0 and 0 on NAND gate. So I think 0 and 0 is 0, complement is 1. So you are going to get 1 as output, 1 and 1 as 0, 0 complement is, sorry, 1 and 1 as 1, 1 complement is 0, 0. And this 1 will comes here, 0 will comes here, 1 and 0 is 0, 0 complement is 1, right? 1, 1. Both the circuits are same. But the thing is, industry having the advantage, they can able to produce only NAND gates. See here, in this particular representation, we have maximum number of 7 NAND gates. Here, this particular representation, we require 3 gates. This is the best circuit. Similarly, if you are going to have any expression in the form of product of sums, so that I can able to represent in the form of OR and circuit representation, right? This is what OR gates, and this is what AND gate circuit representation. When you got this thing, you have to simply do the same process. At the outputs of OR gates, make the complements, and as you put the complement here, if you are going to put complement at the input of AND gate, they are going to be cancelled out. If you are going to put here also, they are going to be cancelled out, right? Now this particular representation, I can be represented in the form of again XNOR gate, right? See, it will look like this, right? So this is x, y. What I can say, this is x bar into y bar. X bar into y bar I can write it as x plus y whole bar. X plus y whole bar means what? This is x nar, which is equivalent to x nar. Observe, which is equivalent to x nar. So I can represent this entire circuit as like this: AC, BD, that's it. So this is the parallel or equivalent representation of this one. So this is what I can call it as NOR-NOR realization. NOR-NOR realization, right? So it is easy for us to implement any circuit with help of in terms of NOR-NOR relation when your circuit will be in the form of OR and representation, meaning that it should be in the form of product of sums. Product of sums, right? Basically, guys, here also, in order to represent one OR gate in XOR representation, one OR gate in XOR representation, you require 3 XOR gates. You require 3 XOR gates. Am I right? I think you require only 2 more. OR gate. OR gate requires 2 XOR gates. So 2 XOR gates. This OR gate requires 2 XOR gates, and AND gate requires, so total maximum of 7 NOR gates are required. Maximum of 7 NOR gates are required. But if you are able to follow certain procedure, you are going to get maximum of 3 NOR gates. So if you would like to convert the same thing, OR and gate circuit into NOR-NOR circuit, you can simply bubble up the outputs of OR gates and bubble up the inputs of AND gate. That's it. So this is the way you can able to convert or you can able to implement NAND-NAND realization and NOR-NOR realization, right? So if you are going to have NOR-NOR realization, compulsory the your circuit should be in the product of sums. NAND-NAND relation, the circuit should be in the form of sum of products, right? If they haven't given, what you can do, you can try to convert it into the respective form. In the last class I have explained, right, how to convert product of sums into sum of products and sum of products into product of sums. I hope you understood, right? Okay, fine. Now let's see. For example, I have an expression f of a comma b comma c, where the function like a plus bc, right, guys? Now the point is here, can you construct this with the help of pure NOR gates? pure NOR gates only, right? So first and foremost point is, if they are asking for pure NOR gates, first you have to check that they are in the form of product of sums or not, product of sums or not, right? Guys, if you observe, is this look like a product of sums, right? So what you can do, you can simply apply again distributive law, right? So if you are going to convert a plus bc, see, a plus bc, you can do it as a plus b into a plus c. Now this look like what kind of expression? This look like, this is sum 1, this is sum 2 and their product, so it will look like in the form of product of sums, look like in the product of sum, right? As they are saying in the form of product of sums, I can represent easily in the form of OR gate representation, OR gate represent, right? Sorry, or AND gate representation, or AND gate represent, right? So try to draw. If you are going to have a and b as input, you are going to, oh sorry, a or b, you got, and then you are going to get ARC. Another one is C with OR gate, with OR gate, and finally you are going to do with AND gate, right? This is what that means. So now to represent the same thing in terms of NOR-NOR gate, what you can do simply, you can bubble up, right? You can bubble up the same thing. So output of the circuit in output of the OR gate should be bubble up. Okay, so A, B, C, bubble up, and the input should be bubble up, right? So guys, if I make bubble up here and if I make bubble up here, is there any problem? No. So I will try to replace this with one more. That's it. So this is the simple logic what you can do to convert, right? So if you want the clarity of outputs, right? So try to take out. This is 0, 0, 1. I am trying to take the values 0, 0, 1. What is 0, 0 with NOR gate? When I am going to give the inputs 0, 0, the output will be 0 plus 0 is 0, 0 NAND is 1, 0, 0, 1, and 0, 1 is 1, so your output is 0, and uh, as I am trying to complement here, it will be 0, it will be 1. Okay, why I am trying to take all the complements? See, you should not consider these complements here because this is normal circuit, right? 0, 0, 1. So 0, 0 is 0 and 0, 1 is 1, 0 and 1 is 0, right? So if you are going to give the same input here also, you have to get the output as 0, right? Try to observe. 0 and 0 is 0, 0 or 0 is 0, complement is 1, 0 or 1 is 1, complement is 0. Now you are going to get 1 or 0 is 1, 1 complement is 0, right? Are you going to get to produce the same output or not? This is what NOR-NOR relation, right? The simple example, right? Yes. Now for example, let me take one more thing. Try to take, we have uh, an expression uh, f of a comma b comma c is equal to a bar b bar plus b bar c plus b bar c. Guys, tell me in which way it is easy to construct like either it is in NAND-NAND relation or in NOR-NOR relation. It is easy for us to construct in NAND-NAND relation because these are available in the form of sum of products. Available in the form of sum of product, right? So basically, guys, before going to construct any circuit, try to make it simplify first. If it is simplified, then we can go for further easily, right? Yes, the expression is already in simplified form, and you can able to construct with help of basic gates, right? uh, if you are going to have uh, the a as input, I need to have the a complement as output, And if you are going to have B as input, you will get B complement as output. For that I am trying to perform AND operation. Okay, this one is done. Next, B complement input, I have to give it to C. See, finally I'm going to perform simply OR operation. That's it. That's it. The same thing. What is the logic I have applied here? See, I don't want to redraw the circuit. Just you can simply make here bubble, here bubble, here you can bubble, here you can bubble, here you can bubble, right? And this like NOT gate you can able to replace with again NAND gates, right? So I will try to redraw A. So this is one NOT gate required. For B also one NAND gate required, and here obviously we are going to have NAND gate. And this input I'm trying to see, I'm just redrawing the same above structure. See, required one more NAND gate, and this will like this. And this entire circuit I can be redrawn as a NAND gate. This is the corresponding NAND NAND realization of the above function. Okay, fine. So let me take the last one. Uh, for example, if you are going to have a function f which is having x, y, z, try to do it x plus y bar z, right? Guys, guys, try to observe in which way it is easy for us. So can we do it with NOR-NOR relation, or can we do it with NAND-NAND relation? Try to observe. I think the same example I have taken here, but it is in the form of complements, right? The same thing, the same thing. So you can do it, convert into product of sums. See, if you try to convert into product of sums, you are going to get x plus y complement into x plus z complement, right? As this is the product of sums, it is easy for us to construct a NOR-NOR relation. NOR-NOR relation, right? But to construct the NOR-NOR relation, first what you have to do, you have to take out the circuit, right? So x is one input, y is one input. I have to have the complement required, and for this I'm going to make OR gate, and the same x I am going to give for another kind of expression z with OR, and finally I am going to perform AND operation. AND operation, right? Simple thing. For this, the parallel equation is, you are going to get x as input, y as input. This y NOT gate I am going to replace with NAND gate. Is it NAND or NOR? NOR, because it is OR and form, right? OR and structure. It is easy for us to convert into NOR-NOR. Okay, so this will be another, right? So it will be represented in the form of NOT gate. I can represent like this NOR. Okay. Now, try to bubble up. If you are going to bubble up, you will get the circuit like this, and Z, the same X you are going to get here. So as you bubbled up this one, this will be modified as like this. That's it. This is the corresponding NOR-NOR realization. NOR-NOR realization. Guys, can we able to construct in the form of uh, like uh, some of the products? Yes, right. This will be in the form of some of the products only. This will be in the form of some of the products only, right? But the thing is, can we do it, right? Try to observe, try to solve, right? I have a like x as input directly, and y as input, that will be having a complement as y bar, and z as input. And how can you get y bar z, y bar z as y bar z as, you are going to have AND gate, AND gate, and from this you are going to be written like this, right? OR gate. When you are going to have OR gate, you will do like this: x plus y bar z. So this is the corresponding expression, guys. But at this point of time, as it is in the form of some other products, and as we represent in the form of AND OR gate, are we going to construct the respective NAND-NAND representation? Try to think. It couldn't possible, because try to observe, if you are going to have the bubble up here, you can bubble up here. Okay, right? Now, can we bubble up here? Can we bubble up on the x side? No, it couldn't possible. Right? So basically, what you can do, you can make up one bubble here somewhere, and you can make up one bubble here, one bubble. So at this particular situation, there is no problem, right? So try to redraw the structure. So x I am going to get the input that I am going to represent in the form of NAND gate, because I first try to do it a complement. Then y, again I am going to do the complement for y. So you are going to get y complement. Here we are going to get x complement. That x complement, see, observe. So this bubble cancel. That's why I made z. For z, I am going to get the data that I bubbled up already. So NAND gate is there, and this entire thing you can represent like this as one NAND gate. One NAND, right? This is the corresponding NAND gate representation for this particular thing. Okay, so try to observe the outputs, what is going to happen. Try to check. So if I am going to have give 0 1 0 as inputs, so don't worry about all these things, because these are for our understanding. 0 1 0, you are going to get 0 here. Obviously when you get 0 on OR gate, if you get 1 here, then only you will get 1, right? 1, you are going to get 0 here, you will get 1 1 1 or 0 0. So total output is 0. Output is 0, guys, right? Can we get the output 0 here? That is what my question. 0 1 1, right? 0 XOR is 1, so 1 will becomes here, and y complement is 0, 1 is as it is. 0 and 1 is 0, 0 complement is 1, 1 and 1 is 1, 1 complement is 0, right? Now both having the same procedure, right? So now these two circuits are equivalent. Right? So this is the way you can able to represent the product, an expression in terms of NOR-NOR relation, and this will be called it as NAND-NAND realization. NAND-NAND, right? Okay, fine. See, guys, if you are able to observe, these are the various kind of representations of the same function, right? The same function, right? This is one way of representation. This is one way of representation. This is one way of representation. And another way of representation is Venn diagrams. I have already shown. Another way of representation is connected diagrams. Yes. And another way of representation is truth table. This is for our understandable truth table, right? If you are going to take the two inputs x, y, z, x, y, z, try to observe what are the possible values for all these. The possible values you are going to get as 0, 0, 0, 1 minute, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, double 0, 1, 0, 1, 1, 1, 0, triple 1, right? See, guys, so what is this x plus y bar z equation? That is what my point here. I'm going to simply divide, right? X plus y bar z. Y bar, see, basically you can do like y bar z again one equation, then you can solve it, right? I will also do the same thing, so it's easy for me to calculate. So y bar z I will first calculate, then I will try to do x plus y bar z. This is my final, right? Y bar z is like multiplication, right? Y bar is 1, 1 into 0 is 0, and this is 1 into 1, 1, 0 into 0, 0, 0 into 1, 0, this is 1 into 0, 0, 1 into 1 is 1, 0 into 0, 0, 0 into 1 is 0. Guys, I made directly, right? Now, x plus y bar z. Guys, as I am trying to perform OR operation, wherever x is there, on OR operation, always you are going to get output 1, right? So that's why I made directly. Or else even 1 or 0 is 1, 1 or 1 is 1, 1 or 0 is 1, 1 or 0 is 1. Now here, try to do an OR operation. So here only you will get 1, and all the remaining cases you are going to get 0. This is the another representation of the same expression x plus y. Guys, actually what we did na, earlier, from earlier onwards I am trying to say, wherever you are going to have ones, once, once, try to take out that as one expression. Try to take out that one expression and try to simplify it, right? See, try to observe. This particular thing, I am going to represent it as uh, x bar y bar z plus x y bar z bar plus x y bar z. See, I am trying to write all the ones, okay? Plus x y z bar plus x y z. XYZ, right? The same expression, right? This is in some of the products. So standard sum of the product, not some of the products also. Standard sum of the products, right? I can represent as summation of 1, 4, 5, 6, 7, 8, right? So like this different ways you can able to represent everything. Okay, fine. So I hope you understood clearly. Fine. Uh, okay. So if anything is there, we'll continue in the next class. Thank you.